In this video, we're going to talk about the covariant derivative in flat spacetime. I've already done 5 videos on the covariant derivative in my tensor calculus series, which covers the covariant derivative in flat space, curved space, and abstract Riemannian manifolds. So you can check the description for links to those videos if you want. In this video, I'm only going to talk about the covariant derivative specifically for the case of flat spacetime. Covariant derivatives in curved spacetime will come in a later video. In my Relativity 104F video, I did a number of examples of taking derivatives of spacetime 4 vectors. For example, I took the derivative of 4 velocity u with respect to proper time tau to get the 4 acceleration a. However, when I took these derivatives, I was working in an inertial reference frame, where the basis vectors are constant everywhere in spacetime. This made things simple because when I took the derivative of a term that was a vector component multiplied by a basis vector using product rule, I could ignore the part of the result that had a derivative of the basis vector. Since basis vectors are constant everywhere in inertial frames, the derivative went to 0 and I didn't have to worry about it. So inertial frames are nice because the basis vectors are constant, and their derivatives always go to 0. However, in non-inertial frames of reference, the basis vectors are changing everywhere in spacetime. In the past couple videos, we've seen that in Rindler coordinates, basis vectors can change size and direction at different points in spacetime. This means that if we need to take the derivative of a 4 vector in Rindler coordinates or other non-inertial coordinate systems, the derivatives of the basis vectors could be non-zero, so we can't ignore basis vector derivatives. To take the derivative of a 4 vector properly, we need to use product rule to differentiate both the vector components and the basis vectors. The basis vectors might change in non-inertial frames, so we need to be sure to include their derivatives. As I've said many times before, basis vectors and vector components are like 2 sides of the same coin. We can't talk about one without also talking about the other. A derivative that makes physical sense needs to take the change of both vector components as well as basis vectors into account in order for it to make sense. In flat spacetime, the covariant derivative just means taking a derivative where we remember to take the derivatives of basis vectors into account. It basically just means we take the derivative properly and don't ignore changing basis vectors. The definition of covariant derivative gets a little more complicated in curved spacetime. But for now, when I say take the covariant derivative of a 4 vector, we just mean that we differentiate both the vector components and the basis vectors. We're going to do 3 examples of covariant derivatives in this video. First, in Rindler coordinates, we'll take the derivative of 4 position s with respect to proper time to get the 4 velocity u. Then, again in Rindler coordinates, we'll take the derivative of 4 velocity u with respect to proper time to get the 4 acceleration a. And finally, we'll take the derivative of a generic 4 vector v with respect to a generic path parameter lambda, and we'll do it in a way that works in any coordinate system, not just the Rindler coordinates. Also, in this video, when I write variables or basis vectors without any markings on top, they represent inertial coordinates, which show how an inertial observer measures time and space. Variables and basis vectors with a tilde on top represent Rindler coordinates, which show how a non-inertial observer with constant proper acceleration measures time and space. And variables and basis vectors with a smile on top represent a general coordinate system, which can be any set of arbitrary curves that form a grid pattern on the spacetime diagram. Before we do any covariant derivatives, let's do a quick review of Rindler coordinates. First, I'm going to remind you that in Relativity 105b, we learned the equations for converting between inertial coordinates and Rindler coordinates, which are the spacetime coordinate system for an observer traveling with constant proper acceleration alpha. Then in Relativity 105C, we learned about the multivariable chain rule, and also that basis vectors are actually tangent vectors along coordinate curves. These two facts allowed us to find basis change equations from inertial coordinates to Rindler coordinates, summarized in this matrix equation with the Jacobian matrix. And we can rewrite all these equations with the standard basis vector notation instead of the tangent vector notation. And we also learned how to do this in the reverse direction with the inverse Jacobian matrix. Now, in inertial coordinates, the four-position vector S equals CT ET plus XEX. But using the change of basis equations I just talked about, we find that in Rindler coordinates, S just equals x tilde EX tilde, with 0 time component. This is because the four-position vector S is always parallel to the EX tilde basis vector in Rindler coordinates. So we can build S completely out of EX tilde basis vectors. And technically speaking, a 4-vector should have 4 components in spacetime, but I'm going to assume that the y and z components are 0 in this video for simplicity, and just use time and x. With the review out of the way, let's take the covariant derivative of the four-position vector S with respect to proper time tau. So basically, we have an observer whose four-position vector S is moving along a world line parameterized by the proper time tau. And we want to find the four velocity vectors u for the observer on this world line. The derivative of S in inertial coordinates is easy, because we only need to take the derivatives of the vector components. The basis vectors are constant everywhere in spacetime, and we could ignore them when we take derivatives. But in Rindler coordinates, the basis vectors can change from point to point. So to take this derivative, we use product rule to get one term with the derivative of the vector component and another term with the derivative of the basis vector EX tilde. The derivative of the EX tilde basis vector is the hard part of this equation. To make it a bit easier, we can use multivariable chain rule to break this derivative down into 2 parts. Our new job is to figure out the derivative of the EX tilde basis vector in the direction of the CT tilde coordinate and the direction of the X tilde coordinate. Remember, using multivariable chain rule, we already found the equations of the Rindler basis vectors in terms of the inertial basis vectors. We can take the derivative of EX tilde in the X tilde direction by subbing in this formula for EX tilde. It turns out that there's nothing in this formula that depends on X tilde. CT tilde does not depend on X tilde by definition, since it's an independent coordinate, and ET and EX are inertial basis vectors that are constant everywhere in spacetime, so they don't depend on EX tilde either. So this derivative is just the 0 vector, meaning EX tilde does not change in the X tilde direction. We can also calculate the derivative of EX tilde in the CT tilde direction. Once again, ET and EX are constant, so we just differentiate this formula with respect to CT tilde. Sinh becomes cosh, and cosh becomes sinh, and we multiply both of these terms by their inner constants, because of chain rule. Now, this big formula looks exactly like the formula for the ET tilde basis vector if we were to divide it by X tilde. So this derivative is just equal to ET tilde divided by X tilde, or in other words, multiplied by 1 over X tilde. So returning to the derivative of EX tilde with respect to tau, expanded using chain rule, we've found this derivative in the X tilde direction is 0, and this derivative in the CT tilde direction is 1 over X tilde times ET tilde. So when taking the covariant derivative and doing product rule, we now know the value of this basis vector derivative. And canceling these X tilde terms, we get the final result for the covariant derivative of s with respect to tau in Rindler coordinates. And this result is not very surprising. It's the exact same formula we would get if we were to expand ds by d tau using multivariable chain rule in Rindler coordinates. We just calculated this same result in a slightly different way. So part of this result comes from the derivative of s's component, and the other part of the result comes from the derivative of s's basis vector. And we need both parts or else we get the wrong answer. As a sanity check to make sure this formula makes sense, we can test it out on our hyperbolic world line, which is a world line with constant proper acceleration alpha. For this world line, ct tilde equals c tau, and x tilde equals the constant value of c squared over alpha. We get the expected result of an observer who has no x velocity, so they believe they are stationary. And the time component of their force velocity is c, which is what stationary observers should have. However, this general formula for the force velocity will work for any world line that we can come up with that is parameterized in Rindler coordinates, not just this hyperbolic world line here. For this second part of the video, let's take the covariant derivative of the force velocity u to get the force acceleration a in Rindler coordinates. So just to be clear, the components of u in any coordinate system are always equal to the derivatives of the coordinate variables with respect to tau. We know this because u is equal to ds by d tau, and expanding its components using multivariable chain rule, the components are just the derivatives of the coordinate variables with respect to tau. Now, of course, taking the derivative of u in an inertial frame is easy, because we can ignore the derivatives of the constant basis vectors, and we just take the derivatives of the components. So we get the second derivatives of the coordinate variables with respect to proper time. But in Rindler coordinates, this derivative is harder. To take the derivative of both of these terms, we need to use product rule twice, to get one set of terms with the derivatives of the components, and another set of terms to get the derivatives of the basis vectors. Fortunately for us, we already calculated the derivative of ex tilde in the previous part of the video. But now we need to calculate the derivative of et tilde with respect to tau. We can use the same strategy as before, expanding the derivative using multivariable chain rule, and computing the derivatives of the basis vector in the ct tilde and x tilde directions. So looking at the derivative of et tilde in the x tilde direction, we can treat ct tilde as constant since it is an independent variable, and we can treat et and ex as constant since they are inertial basis vectors. This means that we just differentiate with respect to x tilde, which means the x tildes in this formula go to 1. And the result we get is just the et tilde basis vector divided by x tilde. As for the derivative of et tilde in the ct tilde direction, we treat x tilde, et, and ex as constant and differentiate with respect to ct tilde. So cosh becomes sinh becomes cosh, and we multiply by the inner constant by chain rule. And all of this is just the ex tilde basis vector, but with all the terms multiplied by these repeated constants and x tilde. So this derivative equals the square of alpha over c squared times x tilde times ex tilde. If we use the definition of the Rindler distance, capital D, we could also rewrite this as x tilde over d squared times ex tilde. So given the chain rule expansion of d et tilde by d tau, if we sub in the basis vector derivatives that we calculated in the direction of the coordinate variables, we get the full expression for this derivative here. So going back to our original covariant derivative of u with respect to tau, we already had the ex tilde derivative from before. And just now we calculated the et tilde derivative, so we can sub these in. Also, if we replace ut tilde with dct tilde by d tau, and replace ux tilde with dx tilde by d tau, and distribute, we get this. So this is our final result for the covariant derivative of 4 velocity with respect to tau in Rindler coordinates. As you can see, the formula is pretty complicated. We get the ordinary second derivatives of the components that we expect, but we also get extra terms because of the derivatives of the basis vectors. Again, we can do a sanity check and test this formula on our standard hyperbolic world line, where ct tilde equals c tau and x tilde equals the constant c squared over alpha. We get the expected result of a constant proper acceleration alpha in the positive ex tilde direction. But again, this general formula for the 4 acceleration works for any world line that we can invent, as long as it is parameterized in the Rindler coordinates. For the last part of this video, let's take the covariant derivative of a general 4-vector v with respect to a generic path parameter lambda, and we're going to figure out the formula in a general coordinate system that doesn't necessarily have to be Rindler coordinates. But before we do that, I really want you to understand that the key for taking covariant derivatives is being able to figure out how the basis vectors of your coordinate system change from point to point. In other words, the key to computing covariant derivatives is figuring out the partial derivatives of the basis vectors with respect to the coordinate variables. We spent the previous parts of this video doing exactly this for Rindler coordinates. We found that the derivative of ex tilde in the x tilde direction is 0, which makes sense since if we look at the ex tilde basis vector in Rindler coordinates and watch what happens if we move along a line of x tilde, the vector stays the exact same. So it does not change in the x tilde direction. And if we watch what happens to the ex tilde basis vector when we move along a ct tilde coordinate curve, we see that the vector begins to tilt in the et tilde direction, which is why the result of this derivative is a vector in the et tilde direction. Also, if we take the et tilde basis vector and watch what happens when we move in the x tilde direction, we find that the vector gets longer in the et tilde direction, which is why the derivative points in the et tilde direction as well. The percentage increase gets smaller and smaller as we move further from the origin though, which is why the rate of increase is 1 over x tilde. The rate of change decreases as x tilde goes up. Finally, if we watch what happens to an et tilde basis vector when we move along a ct tilde curve, we find that it starts tilting in the direction of ex tilde, which is why the result of this derivative points in the ex tilde direction. And we get more and more tilting the further we are from the origin, which is why x tilde is in this formula, because the rate of change is greater farther from the origin. Also, the fact that partial et tilde by partial x tilde is the exact same as partial ex tilde by partial ct tilde is not a coincidence. Remember that basis vectors are really just tangent vectors along coordinate curves. So both of these derivatives are equal to the second partial derivative of s with respect to ct tilde and x tilde. And since the order of partial derivatives doesn't matter, both of these terms are the exact same. If we were to write each of these 4 basis vector derivative terms, each in terms of the 2 basis vectors, we find that the changes of the basis vectors can be described by a total of 8 numbers. In the case of Rindler coordinates, 5 of these numbers are 0. and 2 of the remaining 3 numbers are identical because of the symmetry we talked about before. These 8 numbers that keep track of the changes of the basis vectors have a special name. We call these terms the Christoffel symbols, and they are denoted by the Greek letter capital gamma with 3 indices. The upper index tells us which basis vector they are matched with. So when we see t up top, we know it's paired with the time basis vector, and x on top means it is paired with the x basis vector. The first lower index tells us which changing basis vector we are keeping track of. And the second lower index tells us which coordinate variable we are moving along in the derivative. Each of these 3 indices has 2 possibilities, either t or x. So there are 2 times 2 times 2 equals 8 different Christoffel symbols overall. So when we're taking the derivative of a general 4-vector v with respect to a general path parameter lambda in any coordinate system, here are the steps that we follow. We expand v into its components in this coordinate system's basis, and apply the derivative to each term. We then use product rule to take the derivative of v's components and also the derivative of the basis vectors. We expand the 2 basis vector derivatives with respect to lambda using multivariable chain rule, so that we get 4 derivatives of the basis vectors with respect to the coordinate variables. Finally, we expand each basis vector derivative result, again, into the basis, using the Christoffel symbols as the components. This gives us 8 total terms related to the derivatives of the basis vectors, and 2 terms related to the derivatives of the original components. Of these 10 total terms, 5 of them are written with the time basis vector, and 5 of them are written with the x basis vector. Now remember, the derivative of the time basis vector with respect to x is equal to the derivative of the x basis vector with respect to time, because both of these are just equal to the second partial derivative of s with respect to the x and time variables. We can expand each of these derivative vectors in a basis in terms of the Christoffel symbols, denoted with capital gamma. This means that the Christoffel symbols attached to the time basis vectors must be equal to each other. So for the Christoffel symbols with the t index up top, we can swap the lower t and x indices and get the same result. And the Christoffel symbols attached to the x basis vectors must be equal to each other. So for the Christoffel symbols with x up top, we can also swap the lower t and x indices to get the same result. So even though there are 8 total Christoffel symbols, 2 of them get repeated, so there are really only 6 unique Christoffel symbols. In inertial coordinate systems, where the basis vectors do not change at all the basis vector derivatives are 0, meaning all the Christoffel symbols are also 0. This makes the formula for the covariant derivative significantly simpler in inertial coordinate systems. But in non-inertial coordinate systems, we need to remember to keep track of the changing basis vectors and include the Christoffel symbols in our derivative formula. So when we want to take the covariant derivative of a general 4-vector with respect to a general path parameter in any coordinate system that we want, we use this big formula here, where we need to compute the Christoffel symbols to keep track of the changing basis vectors. So to summarize this video, to calculate the covariant derivative of a 4-vector along a world line in spacetime, we need to remember to use product rule to take the derivative of both the vector components and the basis vectors. And the changing of the basis vectors can be broken up into small pieces, where each piece is a derivative of the basis vector with respect to coordinate variables. And each of these basis vector derivatives can be expanded out in a basis, where the coefficients of these vectors are the Christoffel symbols, denoted with a capital gamma. In this video, we solved for the Christoffel symbols in Rindler coordinates by taking derivatives of the basis vectors written in the inertial basis, and then changing back to the Rindler basis using the change of basis equations. In future videos, I'll show a formula that will let us calculate the Christoffel symbols in any coordinate system using the metric tensor. Now, a couple more points before I finish. In this video, we simplified four-dimensional spacetime to only 2 dimensions, time and x. This meant that there were 2 times 2 times 2 equals 8 total Christoffel symbols. In the full 4-dimensional spacetime, any of these 3 Christoffel symbol indices can be t, x, y, or z. So there are actually 4 times 4 times 4 equals 64 Christoffel symbols in total. It becomes ridiculous to write them all out individually, so in a later video I will show how to use summation notation to make these formulas more compact. Another question you might have is, why is the covariant derivative called the covariant derivative? Well, unfortunately, the word covariant has 2 meanings in physics. The first meaning is in the sense of the opposite behaviors of covariance and contravariance, like when the basis vectors get smaller and the vector components get bigger. The second meaning of covariant just means that something is the same in all coordinate systems, or in other words, something that is invariant. The covariant derivative is about the second of these 2 meanings. The covariant derivative of a 4-vector is the same in all coordinate systems, even if different coordinate systems will disagree on its components. In my opinion, the name invariant derivative would have been better for this concept, since the result is invariant and the same in all coordinate systems. But covariant derivative is the name that history decided on, so that's the name that we're going to use.